Welcome to the deep dive. Today we're going on a pretty massive mission.
You could say that.
We're going to try and chart the huge physical systems that basically run our planet.
Right, from the very center of the Earth all the way up to the atmosphere and the oceans.
The idea here is to give you a really solid grasp of the big picture, a kind of shortcut through the essentials of environmental science.
Exactly. We want to connect the dots between geology, soil, climate, all of it, so you can see how it all works together to shape, well, everything.
Okay, so where do we even begin with something this huge?
I think we have to start at the very beginning, at the core, literally.
4.5 billion years ago.
Yeah, around then. And the entire structure of the planet was decided by one simple rule: density.
Everything heavy sank.
And everything light rose. That's it. They gave us the distinct layers we have today.
So let's run through them. At the very center, you have a solid inner core of what? Iron and nickel?
Mostly, yeah. And then surrounding that is the liquid outer core. The movement of that liquid metal is actually what generates the Earth's magnetic field.
Which is, incredibly important for protecting us from solar radiation.
Absolutely vital. Then you have the mantle, which is the thickest layer by far. That's where all this incredible heat is driving convection.
And then the part we're standing on, the lithosphere.
Right, which is the crust plus that very top sort of brittle part of the mantle.
And it's what's just below that lithosphere, the asthenosphere, that's so interesting. It's not liquid, but it's plastic.
Yeah, that's a good way to put it. It flows just incredibly slowly under all that heat and pressure. And that slow flow is the engine for everything we see on the surface.
Okay, so to get a sense of that, let's talk about hotspots. The Hawaiian Islands are the classic example.
Perfect example. Because here's where it gets really interesting. Your first thought might be that the source of the magma is moving under the ocean floor.
But that's not it at all, is it?
No. The hotspot itself is fixed. It's a stationary plume of molten rock coming up from deep inside the mantle, and it absolutely does not move.
It's the crust that's moving over it.
A crust is the conveyor belt. So the magma punches through, builds an island, and then the plate moves on. The volcano goes extinct, and a new one starts forming over the hotspot.
And that's why the big island of Hawaii is so active right now.
Exactly. It's sitting right on top of that firehouse.
This movement of the crust, of course, is plate tectonics. The whole lithosphere is broken up into these massive plates that are just constantly in motion.
And all the action, all the drama, happens at the boundaries where these plates meet.
Let's break those down. First, you have divergent boundaries.
That's where plates are pulling apart. The best examples are the mid-ocean ridges. As they separate, magma just wells up from the mantle to fill the gap.
And that creates new seafloor. It's called seafloor spreading.
Right. Constantly creating new crust.
Then you have the opposite, kind of. Transform boundaries.
Yeah, this is where the real stress builds up. Think of the San Andreas Fault. The plates are just sliding past each other horizontally.
But they don't slide smoothly.
Not at all. They lock up, they get stuck.
Yeah.
The pressure builds and builds, sometimes for centuries, until snap.
An earthquake. That sudden violent release of all that stored energy.
Mm-hmm. And finally, you have convergent boundaries, where plates are crashing into each other.
And this is where it gets really dynamic.
Oh, absolutely. When a dense oceanic plate collides with a lighter continental plate, it gets forced underneath. That process is called subduction.
And the key thing here is that the subducting plate carries a ton of seawater down with it.
A ton of water. And that water is the secret ingredient for volcanoes.
How so?
As that water goes deeper, it heats up, turns into steam, and that steam lowers the melting point of the rock around it. It essentially makes the mantle easier to melt.
So you get magma?
You get magma, which rises, creates vents, and you end up with these huge volcanic chains like the Ring of Fire around the Pacific.
Okay, so that's the internal engine. Now let's move up to the skin of the planet, the rocks and soil.
The very medium for life.
Yeah.
And it's all governed by the rock cycle.
Which is just this constant process of rocks being formed, broken down, and then reformed again.
Right, and its most important job really is recycling scarce elements. And the best case study for this is phosphorus.
Why phosphorus?
Because unlike carbon or nitrogen, phosphorus doesn't really have a gas phase. It's not in the atmosphere. It is almost entirely locked up in rock.
And we need it for DNA, for energy, for life.
Absolutely essential, but it's really hard for life to get a hold of it.
So how does it get out of the rock?
Through weathering and erosion. Two processes. There's mechanical weathering, which is just physical breakage. Think of ice freezing in a crack and splitting a rock apart.
Like hitting it with a hammer.
Basically,
Yeah.
And then there's chemical weathering, where the rock itself is dissolved, like how slightly acidic rain can carve out massive limestone caves over millennia.
And once it's broken down, erosion carries it away and eventually it settles somewhere else. Deposition.
Yep. Think of shells and coral bits falling to the ocean floor. Over millions of years, that gets compacted into new rock, like limestone, and the phosphorus is locked away again. It's an incredibly slow cycle.
And that slowness is why phosphorus is often the limiting nutrient in an ecosystem, right?
It's the bottleneck.
Yeah.
It's also why we have this whole conversation about peak phosphorus in agriculture, because we're mining it so fast for fertilizer.
Okay, that brings us to soil itself. If you dig a hole, you see those layers, the horizons.
Yes, the O horizon right at the top is all that organic stuff, decomposing leaves, what we call humus.
Below that is the A horizon, or topsoil. That's where most of the roots are.
And the quality of that topsoil comes down to two things: that humus and fine particles like clay.
Why are they so important?
Because they have something called cation exchange capacity, or CEC. It sounds technical, but it's really the soil's superpower.
It's a measure of how well it can hold on to nutrients?
Exactly. Humus and clay particles are negatively charged. Nutrients in the soil, like potassium or calcium, are often positively charged ions or cations.
Opposites attract.
The nutrients literally stick to the soil particles. So a high CEC means the soil can hold on to fertilizer and nutrients near the roots instead of letting them just wash away with the next rain. It's a huge deal for farming.
That's super practical. Okay, let's shift from the ground beneath us to the atmosphere above us.
And how Earth handles all the energy coming from the sun.
You have to start with albedo.
You do. It's a simple concept. Albedo is just the percentage of incoming sunlight that a surface reflects.
So high albedo means very reflective, like fresh snow, right? It reflects something like 95% of the sun's energy.
Right, which is why it stays cold. It's reflecting the heat away.
And low albedo is the opposite. It absorbs energy. Think of black asphalt on a summer day.
It absorbs maybe 90% of the energy and gets incredibly hot. This is why melting sea ice is such a big deal.
You're replacing a high albedo surface, ice, with a low albedo surface, dark ocean water.
And that dark water absorbs more heat, which melts more ice, which exposes more dark water. It's a classic positive feedback loop.
Okay, so now let's talk about the air itself, because its properties create all of our weather.
There are a few key rules. Rule 1. Warm air can hold more moisture than cold air. It has a higher capacity for water vapor.
Rule 2. Warm air is less dense, so it rises.
Always. And as that particle of warm, moist air rises up through the troposphere, it experiences lower and lower pressure.
And when it's under less pressure, it expands.
It expands, and as it expands, it cools down. It's the same reason a can of compressed air gets freezing cold when you spray it. The rapid expansion causes cooling.
So the air is rising and cooling, until what?
Until it hits its saturation point. That's the temperature at which it just can't hold all that water vapor anymore.
And the vapor condenses into liquid water droplets.
And that's a cloud. And if those droplets get big enough, you get rain. That entire process dictates global weather.
So let's scale that up. Let's unpack the huge global circulation patterns that create the world's climate zones.
It all begins with the fact that the sun's energy isn't distributed evenly.
It hits the equator much more directly than it hits the poles.
All that concentrated heat at the equator creates these massive looping air systems called Hadley cells. They operate between 0 and about 30 degrees latitude.
Okay, so at the equator you have intense heating. That means the air is rising a lot.
Aggressively rising. This zone of rising air and low pressure is called the Intertropical Convergence Zone, or ITCZ.
And because all that air is rising and cooling,
It hits its saturation point and dumps incredible amounts of rain. That's why you have rainforests at the equator.
then what happens to that air?
At high altitude, it spreads out north and south. It cools down, and by the time it gets to about 30 degrees latitude, it's cool and dry enough that it starts to sink,
And as air sinks, it gets compressed and heats up.
creating high-pressure zones with hot, dry air. And that is precisely why the world's great deserts are all lined up at 30 degrees north and south. It's not a coincidence.
But it's not a straight north-south movement because the Earth is spinning. The Coriolis effect.
Right. The planet's rotation deflects those winds to the right in the northern hemisphere, to the left in the southern, and that's what gives us our consistent global wind patterns, like the trade winds that ancient sailors relied on.
Okay, from the air to the water. The other massive circulatory system, the thermohaline circulation.
The global conveyor belt.
I like that name. It sounds slow and powerful.
It is. It's a huge, slow-moving current driven entirely by differences in water density.
The name gives it away, right? Thermophore temperature and howling for salt?
Exactly. So you start with warm surface water like the Gulf Stream, moving from the tropics up toward the North Atlantic.
And as it goes north, it gets colder.
And some of it evaporates. But here's the key. When the water evaporates, it leaves the salt behind,
So the water that's left is both colder and saltier.
making it much, much denser. And when it gets up near Greenland and Iceland, it's so dense that it sinks to the bottom of the ocean.
And that sinking is what pulls the whole current along behind it.
That's the engine of the conveyor belt. That sinking water drives a current that snakes all around the globe. It can take 1,000 years for a drop of water to make the whole trip.
And this brings us to one of the biggest paradoxes in climate science, the fear that global warming could cause regional cooling.
It's completely counterintuitive, but it's a real concern. The threat is fresh water.
From melting glaciers and ice sheets?
As all that fresh water pours into the North Atlantic, it dilutes the seawater. It makes it less salty.
And if it's less salty, it's less dense.
And if it's not dense enough to sink,
The conveyor belt could slow down or even stop.
and if that happens, that warm current from the tropics stops reaching northern Europe. The fear is that the region could be plunged into a much, much colder climate, maybe even something like a localized ice age. It's a stunning example of how interconnected these systems are.
It really is. And it shows how fragile they can be, which is a perfect transition to a cautionary tale about human intervention.
The Aral Sea.
One of the most shocking environmental stories of the 20th century.
It really is. I mean, this was once the fourth largest lake in the world, and it basically disappeared.
Because of water diversion, right? In the 60s, the Soviet government dammed the rivers that fed the sea.
They did. The Amu Darya and Sirdarya rivers. They diverted almost all the water to irrigate enormous cotton and rice fields
In desert, basically.
in a very arid region. And the result was just catastrophic.
Yeah.
The sea shrank to less than 10% of its size. The fishing industry, which employed tens of thousands of people, completely collapsed.
And the problems didn't stop there.
No. The exposed seabed was full of salt and decades of agricultural chemical runoff. Now, windstorms pick up that toxic dust and spread it over the whole region, causing respiratory diseases and poisoning the remaining farmland. It's a textbook case of what happens when you try to manage a massive natural system without respecting its limits.
So we've covered the internal engine of tectonics, the surface chemistry of soil, circulation of the air, and the oceans. What's the big takeaway?
I think it's that these aren't just abstract concepts from a textbook. They are the active forces that dictate where life can thrive. They're the reason we have rain at the equator, the reason soil can hold nutrients for our food, the reason coastlines are fertile.
And we have to remember that the Earth itself has these massive natural cycles. It swings between periods of intense plant growth that pulls CO2 from the air, causing cooling, and periods where it builds up, causing warming.
These systems are always in flux on a geologic timescale.
So that leads to a final thought for you to chew on. Considering this huge, relentless natural machinery, the rock cycle, the Hadley cells, the thermohaline circulation, if every human on the planet vanished tomorrow, which of these foundational systems do you think would be the first to start visibly recovering and pushing the planet back toward its pre-human state?
What would be the first sign you'd be able to see? It's the ultimate question of scale and resilience.